Hello, I hope that you've been having an excellent week. I apologize that the tutorial video is a bit late this week. I hope that you haven't been staying up too late and waiting for it. There's a few assignments this week. Assignments 9 to 12 are live. Be careful if you're super fast and you complete assignment 12 in the next few days or the next week or so. We're probably going to add a question part or two to assignment 12. There's a small, I think it was in the follow-up of a Piazza post, but if you haven't read that, there may be another part added to assignment 12 right now that is not there already. Assignment 9 is due on Monday. That's November 16th. You may have heard of the Putnam. It's a math competition. And if you are the demographic for CS145, you probably are in the demographic of enjoying competitive programming or competitive math, or at least know people that do. If you don't, that's completely fine. Competition is probably not the most important thing in the world. It's mostly for fun. In fact, this year's Putnam is only for fun. It will not count towards the total number of Putnams that you are allowed to write. You will not be able to win a prize or anything like that. It's all remote. You can do it from anywhere in the world. If you're enrolled in this university and it's your first undergrad degree, you qualify to write. So just email Jerry Wong. He's a professor here. He's really good. And here's his email. Ask him to put you on the contest mailing list. I hope this is not my PMath student ulterior motive hidden agenda asking you to write a math competition, but Professor Cormack did some advertising for the CS competition. So I thought I would get in here and just let you guys know that this was available. A few students were asking, so I thought you would probably all be a little curious. There's some tournaments in assignment 11. There's one where you have to find the most prime numbers in the least amount of time. Another one where you have to play rock, paper, scissors better than all of your friends. Not for marks, not for competition, for fun. I just wanted to let you know early in case you wanted to maybe spend some more time on assignment 11 than on your previous assignments. For example, if you were doing all of your assignments very close to the due date, you might want to give yourself some more time for assignment 11 if you want to really polish up your rock, paper, scissors algorithm. In terms of content this week, we've got the ordered set and its relationship to A9. Some questions about deferred evaluation will hopefully be answered. We're also going to talk about lambda calculus and the lambda.rkt file a little bit. Here's a question. In assignment 9, there's a lot of moving parts. You're bombarded with stream.racket, ordered set.racket, total order.racket, and you have to write your own main or scoreboard.racket or streaming.racket. That's a lot of files. And it's true. We'll talk exactly about the ordered set and the total order and their relation on the next slide. I just wanted to get some kind of historical development that we've developed over the past couple of weeks since assignment 3 till now to hopefully get you centered to what this idea means. So on assignment 3, we learned how to build undecorated binary trees, and that was great. And they were super mathematical, super basic. We were maybe not basic, elementary, but not easy. Assignment 4, we decorated them. So we've taken our undecorated trees and we've added one more field and brought our abstraction up one level to be a bit more useful for us if we want to store numerical information. Next, we learned how to build minimal height BSTs. So these are trees that we can run many operations very quickly because many of the operations that we're interested in take time proportional to the height. In A6F, we learned how to build an efficient set by using an AVL tree, which is kind of similar to the ordered set that's on the assignment. In A67, we learned how to use that ordered set to do some practical work by storing some card data to make our program more faster. And now in A9, we finally have an ordered set that can take anything in. And there's a bit of an asterisk next to anything. Any data structure that you can define in Racket for which you can define a total order and a few other things, including a predicate and an associative operation. This still gives you a lot of leeway as to what you would like to include in your total order. For example, almost all of the compound data that Professor Cormack talked in assignment 20 is fair game to put into your TO rep or your 2 rep in total order.racket. Ordered set is very similar to A6F, but instead of taking numbers as the set element, it will take in whatever you define in TO rep, so, or in total order.racket as your TO rep. So this file is basically your answer to the question, what is the fundamental unit of my set? What is my set containing? Whatever is in total order.racket. You can see how this might be useful for keeping track of the numbers and then some other data about the numbers for assignment 9B. And then for parts C and D, you can keep information about the players and their earnings in your ordered set so that you can access them in logarithmic time. We understand the stream as a lazy list. What that means is it's a list, but the rest of the stream is deferred. And we're going to talk about exactly how the rest of the stream is deferred in a couple slides. Some of the tutorial content is very reactionary. So the most frequently asked questions and the most common mistakes that we see through the week will usually make their way into a tutorial video. And this was a big one, and it's a very good question. And it's also here because it's very good to understand this kind of thing, just in terms of maybe intellectual satisfaction. So the first question, what do we talk about when we say promises? So this is when we wrap our expression in a lambda. And here's our expression, expr, and here's our wrapping lambda. And you can see it's a parameterless lambda. This, in racket, in full racket, you'll notice that this defers computation until you call it using brackets, until you say, evaluate this lambda and give me the expression. It won't compute what's inside of the expression. We're going to talk about why on the next slide. Big O runtime is a bit more complicated in computing it because we don't calculate everything at once. For example, in stream generate, you'll see that the whole rest of the list isn't actually calculated. All of the elements are not actually calculated when you call it. That's why you can often get it to run in O1 time, but stream_coulter will take, for example, logarithmic time or linear time. Here's the observation we had with promises. And then now we're going to see exactly how does this work. So here is the answer to why does wrapping it in a lambda actually stop the computation? Why would we want to do this? Well, evidently we can't compute the sum of x and y without knowing what x and y are. This is as much reduction as we can do, plus xy. Making it a function, an anonymous function with a lambda, doesn't really make our situation any better. We still have this plus xy that we can't evaluate. Same thing goes for just one parameter. We can't sum x and x until we know what x is. Racket doesn't treat this case any differently from the above case. Even though x doesn't appear in this expression, it still says, well, I can't calculate this expression body until I know what x is. And so that's why it defers this computation right here, because it says, well, I can't evaluate this until I have my parameter. I don't have all the information. Parameterless lambdas, though, are not treated any differently. So lambda of nothing, no parameters, plus 4, 5 will defer the computation of adding 4 and 5 until it's called using extra brackets. And you can notice that this is exactly the same form as in the previous slide. This is wrapping our expression in a lambda. So we're promising it, we're promising to compute it, and then we actually go to compute it when we call it with the extra brackets. In stream.racket and stream generate and stream car and stream coulter, you'll see this behavior in the implementation, and I encourage you to look at the implementation. The AVL tree was not really a necessary implementation for kind of your satisfaction as a computer science student in this course, but I would say that understanding stream.racket and total order.racket will definitely help you with your satisfaction in this course. So if you look at the implementation, you can pull it up right now if you want. Stream car will get you the stream pair this, and stream coulter will evaluate the promise in stream pair next. I think something just happened on my computer, so I'm going to make sure we're still recording here. Okay, everything looks good. again, somehow we got off track. I'm really sorry about that. This is the slide that we were on. I'm sorry about that little delay. Stream_cdr, as I was saying, will evaluate the promise of stream pair next. So you'll see these extra brackets calling in stream_cdr, and you'll see them as well in stream_generate. You'll see that making the rest of the stream is wrapped in a lambda. It's promised. You don't compute the whole stream. That's why the running time is only 0.1. And you can dig into all of the other ones and check them out. And the practice problems, you may have seen them. I flashed them for a couple seconds accidentally there. Really are trying to get you to dig into this idea. Lambda calculus, it's a model of computation. It's a mathematical construct. It is a figment of your imagination. It's a way to compute everything. Professor Cormack mentioned in lecture that it's mainly considered some kind of pen and paper computer language. It's just a set of rules for substitutions and lambdas. And with this set of rules, it was picked so cleverly that you could compute everything. That's the short story about it, at least. Important to know are the definitions in lecture, and this goes hand in hand with this little hint that we'll get to. Things like true and cdr and char and list and numbers are all essentially abstract data types, and it doesn't matter how they're implemented so long as they work. There's nothing fundamentally true about lambda x, lambda y, lambda x, and there's nothing fundamentally false about lambda x, lambda y, y. But if we take the convention that true and false are defined that way, we can use them as selectors. We can differentiate them. One's got an x, one's got a y. So true and false are not the same thing. But functionally, that lets us use them as true and false. So one of the primary uses of true and false in computer science and programming in Racket is to say, well, if this is true, then I want to do something. And otherwise, I want to do something else. And from that fundamental if is kind of how we've decided to implement our true and false. We've decided to take a working programmer's definition of these things, and we'll give them the definition that gives them the right behavior if we substitute them into an if. So if you pass a Boolean value like true or false, and then the true part and then the false part, true will select out and compute the true part, and false will select out and compute the false part. Again, there's a little asterisk next to computes, because if you're in a lazy language, the computation itself might be deferred later on. Definitely take the time in lectures 26 and 27 to try to understand what all the lambda calculus definitions of things like cdr and char are about. You'll see that cdr and char are also implemented using true and false for exactly the same reason. Char is just selecting the first thing, because all the lists in Racket are essentially just the first element of the list and then the rest, and then cdr is just selecting the second thing, which is the rest of the list. So there's a parallel between the if definition of true and false and then our chars and cdrs. We express recursion in Racket using the Y Combinator, sorry, in lazy Racket, in lambda calculus using the Y Combinator. It's a very subtle topic. As Professor Cormack said in the lecture, you might want to read up on your own if you're concerned with really getting deep into this fixed point combinator and how it works. In a future tutorial or post, or potentially one of the visual problems, I will try to dig a bit deeper with the Y Combinator and why it works in lazy Racket and why it doesn't work in strict Racket. If you've seen the beta reduction of the Y Combinator, you'll see that y of f reduces to f of y of f, and then in turn, that reduces to f of y of f. So that's why it doesn't work in strict Racket. The other one is a bit more subtle, and hopefully we'll get to that in the future. Here's my hint. Try to read and understand every function in lambda.racket before you start A10. These are all things that will help you through A10. And they are essentially implementations similar to the ones that Cormac has shown in lecture of all the constructs that we've made in lambda calculus A debugging tip is to write the functions using the understandable concepts from the file we give you, as in using add and mul and plus. I don't think we give you mul because that's an assignment problem, but using what we give you and then translating them into lambdas will help you with debugging. It's going to be very difficulty. It's going to be of high difficulty to write 20 lambdas in sequence with the right parameters in the right order that you need to create the functions that we're asking. So try to either plot it out on paper or plot it out using understandable human expressions before you go down the rabbit hole of writing it in lambdas. Here are the practice problems. It's kind of less of a set of practice problems and more of a little project. And the idea of the project is to understand deferred evaluation and Big O runtime and how they interact with each other. So the parts highlighted in blue are the actual questions, and then the black is kind of the tutorial equivalent of the assignment preamble. So I'll read the questions. Define a function buildStream funExter that consumes a function, initial value, and stream. The second problem is to determine the Big O running time of streamcar and streamcdr. Of course, applied to streams that were created by buildStream. And you're saying, what is buildStream? BuildStream for me is a function that outputs a stream with nth element equal to the full del of the function, the accumulator, and then the first n elements in the stream. To put this another way, the nth element in the stream is what you get after you fold the first n elements. The next problem is to determine the Big O running time of streamcar and streamcdr. You can assume that your function is O of f of n, and it might also be useful to try to solve this for, say, an f that runs in linear time with respect to n, an f that runs in constant time with respect to n, and an f that runs in logarithmic time with respect to n. Put another way, I want you to find the running times of the nth applications of streamcar and streamcdr to a stream produced by buildStream. We don't really care about finite streams as much as infinite streams for the reasons that we could just use a list. So you don't have to worry about running to the end of the stream and then having constant time or zero time because you stream generate, you run out of elements in your stream. You don't have to worry about that kind of philosophical rabbit hole. Just stick to the infinite stream and the nth element. If you don't want to do this first part, or you want to check your work for this first part, I've included an example program with the first part and a couple examples of actually using buildStream. It might also be good to take a look at it if you don't really understand what I'm trying to ask you here. The link is in the description. Just as a quick recap of this problem, I'm asking you to build kind of a folding function for streams that will produce different stream elements by folding at each level of the stream. So if, I know I said we don't really care about the finite version, but the finite version is a little bit better for explaining. So if I had the first, if I wanted to buildStream with a stream of 10 elements, say the numbers 1 through 10, 0 and plus, that would just give me, my first element would be full del with plus 0 and 0, or the 1, so the numbers from 1 to 10, which is just 1. And then my second element would be full del with plus 0 and 1 and 2, which is 3. And then you could see that these will actually give you the sum 2 numbers, the triangular numbers, at each step of the way. So the first 10 triangular numbers. And that is actually the example that I've included in buildstream.racket. It might be a bad name because it doesn't correspond exactly to buildlist.racket. If there's something already called buildstream.racket, I apologize for calling it buildstream.racket. Hopefully that won't be too much of a conceptual hurdle for you. It's been a great week. It's been a long week. You deserve rest. So hopefully you can get some sleep this weekend. And again, start your studies on Monday morning as a happy and healthy human being. Thanks for watching, and I'll see you next time.